It's a great honor to speak here at this event in memory of Jan Nikor, who in his mathematical and in his personal life touched so many of us. Maybe some of you wonder about the title of my talk, because it's maybe a bit different from previous talks. But don't worry, there will appear some p-adic cohomology theories. This is joint work with Jan Chin and Timo Keller, who previously worked on the L-adic part, and I joined them for the p-adic part. So let's start by setting up some notations. Or maybe I should say, I'm quite new to this type of questions, so please be gentle with me and also tell me if I'm telling you too basic things. So small k should be a finite field of characteristic P. Wk will be the ring of Witt vectors of small k. And K0 the fraction field of Wk. Then I consider the following situation. S should be a smooth projective irreducible variety over small k. And I denote by Ks its function field. Now I want to consider a smooth projective variety over Ks. And I think most of the time I need that it's geometrically connected. So we are interested in invariants associated to x over ks. However, very often it's not possible to describe them just in terms of x over ks, but we have to use a smooth model. By that I mean a smooth projective morphism from curly x to u, with generic fiber x over ks. Okay, so maybe I leave this here. So first I would like to recall the definition of L functions, and at the moment I will use the L-adic definition. And already here, so we would like to have invariants that are associated to x over ks, but already here I have to use a smooth model. So I define the nth L function. Probably all of you know this definition. as the product over all closed points. So this is a very, very standard definition. I just want to recall it. Where here I put the SQL sheaf.
Veronika, Mark is asking about the relation between U and S.
The function field of U is equal to the function field of S. So this is the generic fiber of this morphism is the morphism from X over Ks.
And mu is not S.
This is U. No, U is not S. U is an open subset in general. We can obtain such a model by spreading out, but we cannot obtain in general a model of all over S.
So U is an open of S.
Yeah. Okay, so as we are interested in X over Ks, really, this definition uses obviously the model, but we still can extract information of it that is independent of the model. And here the following fact, which I think was proved by Tate, is particularly important for us later. Namely that in a particular strip, the zeros and poles of this L function are independent of the choice of a model. So okay. So I promised you that some periodic homology theories will appear. So we have to think about what periodic homology in the context of a variety over a function field means. And that's what I will define for you next. We are working with rigid cohomology. And what we would like to do is to work with higher direct images. Ertl defined this in terms of the RAM complexes of rigid spaces. And he conjectured, so this is Berthelot's conjecture, that they should have a canonical structure of an overconvergent F-isocrystal. And as far as I know, this conjecture is still open. So we have to think about something else. And fortunately, there is a theorem which was proved by Ambrosi. So we could consider August's overconvergent F-isocrystals, overconvergent push higher direct images. And Ambrosi showed that if under the functor, the canonical functor from overconvergent F-isocrystals, August's higher direct images have a pre-image. And because by Kettler's theorem this functor is fully faithful, we know that this is unique. So we can just work with this pre-image for the construction, at least, without worrying about what it really is. So I will use, just so that we know, I will just use the same notation, almost the same notation. I will write this pre-image as like this.
So the convergence structure is not enough for you, you need to overconverge everything?
We need overconvergence since we are working over an open base. And we want to have cohomology theories in overconvergent F-isocrystals. Okay.
So is it compatible with Berthelot higher direct images, or there is some problem to?
There's some problem. That's not, but because otherwise we could solve Berthelot's conjecture. So now we can use this to define the rigid cohomology of x over ks. So that's what we want. So I use this notation to make sure to keep track of the fact that x is considered over ks and our coefficients are in k0. And here will appear something. So for a given model, we will just take this, and then we take the limit over all models. And Pal showed in a recent paper that this is almost a Weyl cohomology, so it has properties as nice as one can hope for. So in particular, of course, one has to show functoriality and that it's well defined and it has values in F isocrystals. Cup product and Kühnen formula. And finally, most important probably for the rest of the talk is that it has a cycle class map. So this was shown by Pals. Maybe I should mention that to construct the cycle class map, it is in fact not enough to consider the preimage of the August-Higher direct images. Because to use this, to construct this, one needs a Lorentz spectral sequence. And one can do this, of course, if X is nice enough, and if the model is nice enough, so if we have a model or if we have a nice enough compactification. Another way is a way to get around this is one has to use she who proved that after shrinking the base, which of course we can do because we don't really care about the model, and taking an alteration, then it's more or less has an overconvergent structure, and then one can use this to to construct the cycle class map. And I think she who calls this generic overconvergence. Okay.
Almost means that it misses functionality.
Yes.
Okay.
And this result of Ambrosi you mentioned from which year? Do you remember when it was shown?
Ambrosi, it was quite recently, so I think Lasta had a proof in 2016, but apparently there was a problem, and then Ambrosi showed this a couple of years later.
So in definition, the column is taking over all the model and then taking over all the open view.
Yeah.
Okay.
Yes, you have to show that you have a co-filtered category.
And so in particular, the groups are the finite dimensional, like the case
Yes.
there.
Fully meets some stabilizers.
Yeah, you have. Yes, you can show that they are all for each choice. They are all isomorphic.
Choice of what?
For all choices of models. For all choices of models.
Ah, okay, because you shrink to the. Okay.
Yeah, it doesn't. So for the cohomology theory, it doesn't matter. But to have, so in principle, you could just choose one and work with it. But to have a canonical definition, it's better to take the limit.
So could I ask a quick question? So do I understand correctly that, for instance, if I took a curve, then the dimensions of these cohomology groups will be generally not what I expect it to be? Like they will not be 2G, the genus. It just seems like you only pass to some part of the, like if I wrote down the Laurent spectral sequence.
Yeah, that's right. Yes. Yeah.
What did you say? That it's not.
Like the H1 would be general less, the dimension will be less than 2G.
Why?
I mean,
I was wondering, but.
I mean, you have the edge map from the cohomology theory of curly X to the other one.
So Poincaré varieties is false.
I don't know. Paul didn't prove it, so maybe it is just very difficult to prove. We didn't try to prove it because we didn't need that. But Paul also doesn't need it, so he also doesn't prove it. I'm not sure. I don't know if it's false.
So the H0 is not with connection. I mean, which kind of H0 you take?
The Gauss-Manin connection.
Ah, okay. So this picks only a small part of the.
Yeah.
It's so the dimension, or like what we said, the dimension is not.
Okay, so now we have this cohomology theory, and of course, the first thing that we can do already with the higher direct images is we can define the L functions also using the rigid higher direct images, and of course, so I think this follows from the proper base change theorem that all of the L functions coincide. Okay, now I would like to recall some conjectures by Tate, which he formulated in the 60s. And he wondered in particular about the relations between these conjectures and proved some relations over finite fields, so not over function fields. And we are in particular interested in these relations over function fields. So the first one is usually called the BSD-rank conjecture. So I denote this for like this. And it compares the analytic rank and the algebraic rank of X. So this is defined as the order of S at the point dim S of the first L function and here we need in particular that this is independent of the choice of a model and this is equal, should be equal to the algebraic rank. Which is just the rank of the peak zero. Okay.
So before you got this off, you were saying you can replace the analytic higher direct image by the over conversion gadget. Are you saying that doesn't change the L function?
Yes.
Okay.
That is also in Paul's paper.
Okay.
So the next one is the Tate conjecture. That I denote. So I only write down the divisor case because that's the case that we are interested in. I denote this by T1 x over ks. And this depends, the formulation depends on a prime L. But now in the formulation, of course, we have to differentiate between L equals P and L not equal to P. Because we will use different cohomology theories. So we consider the cycle class maps. So first the LAD case. And in the PAD case, we have the rigid cohomology that we just constructed over there. And the conjecture says that these maps are surjective. Now it turns out that for varying L, all these Tate conjectures coincide. And the proof for this passes through another conjecture.
So here one has to know that the line bundles which are algebraically equivalent to 0 goes to 0 in the under gamma x. You have to know that it factorizes through Néron-Savary.
Yeah, one has to show this, yes. But it does. Yeah, I mean, that's not only true for the case, I equals to 1, that's true in general.
But to formulate the surjectivity, you don't need that.
No. I mean, you can also work just with the pick. Okay, so the proof that all these conjectures are equivalent passes through another conjecture. So I don't know if it has a specific name. Namely that which I denote by just T x over ks without L, because it's formulated without the L. And it says that we have an equality between the dimension of the Nero-Severi group and now the order of S at dim S plus 1 of the second L function. No, minus. And again, this is independent of the choice of a model. It was shown by the LAD case was shown by Pal and by Tate, and the PAD case was shown by Pal, namely that we have an equivalence for all primes L. L2 is the second L function.
Is what?
The second L function.
Did you see the same?
What do you mean?
What's the second L function? Could you say?
Now we are interested in the relation between the Tate conjecture and the BSD-rank conjecture, which I unfortunately just erased. And more precisely, we are interested in the obstruction of these conjectures. And the relations. So the obstruction of the Tate conjecture can be given in terms of the Brauer group. We have the following, there is the following theorem. We have the following equivalences. First, the Tate conjecture. Now the finiteness of the L torsion subgroup. So we only have this this, or I will talk about this later, but this equivalence here only holds for L is not P. And this was well known for quite some time, this equivalence, and now the last one is the strongest, I guess. Namely that the non-P torsion subgroup is finite. And the equivalence of the last two was proven by Kadore, Hui, Tamagawa. It turns out that we have a similar picture for the BSD-rank conjecture. In that case, we consider the Tate-Shafarevich group. So we have the following equivalence. Here you will see that it's quite similar, and here the good reduction case was proved by Keller and the general case by Chin. Again, the first statement is the BSD-rank conjecture. Sorry, I have to make some assumptions. This is not true in general. For an abelian variety. So I don't... Here I assume that what I called X before is now an abelian variety. And second, I have almost the same statement as here, just with the Tate-Shafarevich group. And again, here we have the non-P torsion part for L not equal to P.
What is the definition of sharpness when S has dimension bigger than 1?
Yeah, I really find it as follows. So I think this definition was first considered by Keller. And here I'd consider the codimension 1 points. Sorry, now it becomes too small. So this thing here is the fraction field of the strict tensor of the local ring of OS. And A. And actually, in the L-adic case, in the P-adic case, this doesn't have as good properties as in the L-adic case, because here we have things like invariance under rational birational morphisms, and in the P-adic case, one has to modify the product slightly to have good properties of this.
So do you take so this depends on the model?
Yeah, but one can show that after taking, that if you only consider the L torsion part, it doesn't depend on the model anymore. If you only consider the L torsion part, it doesn't depend on the model anymore.
Even if you shrink the model so that you have less codimensional points?
Yeah, I'm not sure about this. At least in the P-adic case, we had to modify this. So we had to use the divisorial valuations here instead. But I think this was shown by Chin that if you take VL of this, that you can shrink the model. The rational Tate module.
Ah, okay. So the finiteness is independent of.
Yeah, the finiteness is independent. Sorry.
And in the usual Shafarevich group for over a number field or function field, you use initialization or completion and not strict initialization. Does it change the notion here? So you consider torsors like over Q, which are trivial over each QP, and here you consider QP strict initialization, which so it's apparently it's bigger because it's changed. It could change the. I don't know. It seems to be different conditions.
Yeah, but we only care about the finiteness.
So the finiteness should be similar.
Yeah, the finiteness is simpler. Yes, sorry about that. I mean, the statement is that the finiteness is independent of the choice of the model. So that's a much weaker statement, I think. Okay. So now we can relate these two conjectures via their abstractions, and Quinn showed the following.
Could you say again why you take this SHA and you don't take the usual SHA? That's the kernel of all the usual localization.
Because so this gives us the invariance of the finiteness under the models.
Okay, it just works for this one.
Yeah. So we have to assume that the Tate conjecture is true for the base. Then we have a short exact sequence. And of course, as you noticed in this picture, the p-adic part is missing. So that was what we were interested in. In particular, we were interested in a similar statement as this one for the p-adic part. So for simplicity, I will assume now that we are in the good reduction case. One can use resolution of singularities in characteristic P without assuming this. However, this is not ideal, and it doesn't really give a hint how to do the general case. So let me, for the moment, focus on the good reduction case. So by this, I mean that we have a model over all of S. And in this case, we have the theorem. So you will notice a difference to the previous one. Again, we assume that the Tate conjecture is true for the base. Then we have a short exact sequence. And here we do not identify the obstruction of the Tate conjecture precisely. We just say that we also just use in the proof that this is the obstruction of the Tate conjecture.
as in Picard, is still Picard or
Yeah, it's pig knot. It's pig knot. Sorry. Okay, so let me say a few words about the proof. So as we are in the good reduction case, we have the degeneration of the Leray spectral sequence for rigid cohomology. At the E2 page, and this gives us short exact sequences. So we also have the FPPF Leray spectral sequence. I use both of them to get the short exact sequences. So this is just the usual rigid cohomology. I just keep also track of the base here. So here, this is all induced by the cycle class map. So we know that the obstruction here is this. Here, it turns out that this map is injective. And the heart of the proof is to show what the co-kernel here is. And in fact, here, this is exactly what we want to have in the sequence. And the proof is, so this is the most technical part of our proof, it uses some arguments of Bauer, who treated the case that S is a curve, which we had to generalize to higher dimensions. Okay, so using the snake lemma, this then gives us short exact sequence like this. But now this vanishes because of our assumption, so we get an isomorphism here. But we can identify this with the kernel of this map. So more precisely, we have a diagram of short exact sequences. And the last one is the one we are interested in. And this gives us then exactly the exact sequence that we want, because here is the co-kernel that we have written here. Here is the co-kernel, here is the VP of the Brau group of curly X, and here is the co-kernel of gamma X. So basically here now you can using the snake lemma, we obtain the short exact sequence that we wanted. So maybe let me say a few last words. In our statement, we just used that this is the abstraction of the Tate conjecture. We didn't use anything else. So it would be really nice to be able to identify this in order to have more tools at our disposal, with which we would then be able to generalize this to the non-good reduction case without resolution of singularities. Yeah, so this is the gamma x, because here you have the curly x and here you have the other x. That's the one that I used here, which I identified before with this VP SHA. So here we will get the VP SHA. Here we have the VP of the Brauer group of the curly x, and here we have the abstraction of the Tate conjecture of x over ks. Should I write it? Okay, then let me stop here. Thank you very much.
Any further questions?
Let me ask you one question. What's the benefit of using rigid cohomology over arithmetic module? I think you have more tools.
Yes, so I mean, our goal is to generalize this to not good reduction. So we have to work with cohomology groups that are finite, even though you are working over an open base. Yeah. And then you have more tools to do that.
Now I think he's asking what's the advantage of doing p-adic versus l-adic?
You mean p-adic versus l-adic, or?
Arithmetic P module. Why don't you use it? I mean, you have more tools. So you don't need to worry about this kind of come to reality.
I guess we wanted to have an analog of the l-adic case. And
can you really do this with arithmetic D modules?
Excuse me?
Can you really do it with arithmetic?
Yeah, I guess so.
Really?
Yeah, maybe we could talk later about this, because that sounds interesting.
I wanted to ask one question actually. So we're supposed to believe the Tate conjecture for our model X. Mm-hmm. So then we should deduce that the co-kernel vanishes, which tells us about the vanishing of some p primary torsion in some SHA, right? But it seems that then it doesn't quite give us BSD, right? Because we don't yet have a p primary form of the theorem on the board up there. Is that right?
So what we can deduce, for example, if we have an abelian variety, which means that this would vanish, that if you have an abelian variety, A over Ks, then this vanishes.
Right.
Then you get an equivalence between the two.
Right, but then what does the vanishing of the left one tell us? Let's assume the middle vanishes. We will believe that.
No, I mean, we are just claiming the equivalence. So we know the equivalence for the l-adic case.
Right, but here we've got some p-adic information about SHA.
Right. So yeah, you will get exactly the same here. Because you can, once this vanishes, yes, all the Tate conjectures are equivalent for different primes. So then you can pass to the l-adic case. Okay. Yes. And then you can use the l-adic case to get the exact same equivalences for the p-adic case.
Okay. Yeah, okay. And should the p primary torsion be finite too?
Or finite exponential.
Sure. Should it?
Yeah.
Yes, I am the chairman. Is there any further? There's nothing further than we thank Veronika again. We started at 2 o'clock.